Hey there, welcome back to Short Text 331. Today we're going to talk about roots on the complex plane. And this is the continuation of our roots in 2D discussion, where now the 2D is going to be the complex plane. So suppose we want to solve for z here in this equation. So we have z squared minus I equal to 0. And by the way, this is generalizable to any function of a complex variable. And you can always write such a function as a real part and an imaginary part. And so this is going to be then a g1 of xy plus I g2 of xy. So then g1 encodes the real part and g2 encodes the imaginary part. And of course, I didn't say it, but z here is x plus iy. So x is the real part and y is the imaginary part of z. And so we want to find then the roots of this equation in the complex plane. Now this can be solved analytically, of course. It's a very simple case. It's just an example, but let's see how one would do this numerically. So the first thing you want to do is to identify exactly the real and imaginary parts of this function. And so here, the only complication is taking z squared, so it's x plus iy squared, and so the result of that is x squared minus y squared plus I 2xy. And so the real part then is x squared minus y squared, and the imaginary part is 2xy minus 1. So this minus 1 comes from this minus I here. And I emphasize always in my courses, when people are learning complex numbers, never forget that the real part and the imaginary parts of a complex number are themselves real numbers. So when we talk about the imaginary part, we don't include the I in the imaginary part. So it's always just the coefficient in front of the I, or the coefficient that comes with the I. But the imaginary part itself, so this G2, for example, is a real number. It's itself a real quantity. And so then we're automatically in 2D. We're therefore looking for the point xy such that g1 of xy and g2 of xy vanish simultaneously. And so we're in 2D, as I was saying. And so we want to use two-dimensional Newton-Raphson. And so we want to solve for these two things simultaneously and want to find the point xy that satisfies these two equations simultaneously. And so we use the notation of the last video. And if you haven't seen it, well, you can stop this video here and go ahead and watch the previous video, roots in 2D. But the way we set up the problem is like this. First, we have our function or our vector f encoding the function for which we want to solve. So, or rather, the function that has to vanish, the function whose root we're trying to find. And that function has a g1 and a g2, then two entries, which are going to encode the real part and the imaginary part of the function, of the original function that we called here little f of z. So real part, imaginary part, those go into the entries of this vector. And then we're going to define a vector that I called x here with a vector on top, an arrow on top. It has entries x and y. Those are encode our point on the complex plane. And then we have to build this Jacobian matrix. So the matrix of first derivatives of this function. So then we have dg1 dx, dg1 dy, and then the second row is dg2 dx, dg2 dy. For our case in particular, for our function x squared minus y squared plus I2 xy minus I, so all this stuff, z squared minus I, that's our function. In that case, our derivative is dg1 dx is 2x, dg1 dy is minus 2y, dg2 dx is 2y, and dg2 dy is 2x. So the fact that these cross derivatives here are equal and these two are differing by one sign only is a reflection of the fact that this function f of z is what's called in complex analysis an analytic function. So an analytic function has to satisfy necessarily the so-called Cauchy-Riemann conditions, which give us that dg1 dx has to be dg2 dy, and dg1 dy has to be minus dg2 dx. And so this is correctly satisfied here. It's not needed for us to be able to do what we're trying to do here, but it is part of the properties of analytic functions, which is what we happen to have here. And now what we need to solve to implement Newton-Raphson is to solve for the update. So to solve for this delta x, and that amounts to taking j and putting j on the other side of the equation. So we have to solve this linear problem. Matrix times vector equals minus this other vector of functions g1, g2. So you have to solve this for your starting point x0, meaning you're going to evaluate this matrix at its starting point, you're going to evaluate f at that starting point, and you're going to solve for this quantity delta x, which will give you delta x and delta y for your problem. And once you have that, then you can update and move in x and y using this simple formula. So the new point is the previous point plus this delta x in x and y. So fortunately for us, this is just a 2x2 problem, so we can use the so-called Cramer's rule, which tells us how to solve the problem. So if we want to solve for delta x, all we need to do is we need to know the determinant of j and divide by that determinant. We're going to be dividing by the determinant of this matrix. And then we need to go into this matrix j and replace the first column by the right hand side. And so our right hand side is minus g1 minus g2. Remember, our right hand side is minus f, and so we replace that, and we leave the other column intact. So dg1 dy, dg2 dy, which is what we have here. And so we calculate this determinant, we divide by the other determinant, this is the result, and that will give you delta x. So now I wrote this entirely in terms of g1 and g2. I didn't say what the function was. So this will be valid even if your function is not just z squared minus I. So this will be valid for other functions as well. If you have z cubed, z to the fourth, some other complicated function, this will still hold, and you can use this. And the same with delta y, except that you replace the second column, and so you take this determinant, and if I did everything correctly, this is the result, divided once again by the determinant of j. The determinant of j itself takes this form, which for the particular function that we wrote, that we have z squared minus I, it takes this form. This is the determinant for x squared plus y squared. Unless I made a mistake, I think this is correct. And so if that's all true and that's all fine, then these formulas will take you there, will allow you to calculate delta x and delta y. Keep in mind, all of these, including the determinant of j, are functions of x and y. So you're going to need to reevaluate this every time you update your point. You go from x0 to x1, and you need to recalculate everything to calculate the new delta x and delta y. And with that, you can update x1 to be x0 plus delta x, y1 to be y0 plus delta y, and then once you update this, you go back to the beginning and you recalculate everything. And you keep doing that, and keep doing that update. And as you can see, the most expensive part of the update is calculating these objects here, because you need to do those every time you update your point. And so when do you stop? So you can use as a stopping criterion the magnitude of your function f of x, y. So I wrote here f of x comma y, I mean f of z. What that tells you is the magnitude of the real part, the magnitude of the imaginary part. We want these two to go to 0, and so this type of function will vanish when both of them vanish. And so this will approach 0 as g1 and g2 simultaneously approach 0. And so that you can use for a stopping criterion. For example, your stopping criterion could be that you're going to be doing this loop on and on and on until this magnitude of this function, so this combination here, is less than 10 to the minus 3, say. You could have something like that. And that's it. That's about it. That's all you need to know to carry out finding roots in a complex plane. Again, this whole thing will depend on how complicated your functions are, g1 and g2, and their derivatives. If they're very complicated functions, then this will be a more expensive step. For polynomials, this will be pretty easy, however. Finally, something very interesting about this type of problem with polynomials in particular is that you can plot in the complex plane for each given point that you use as a starting point, you can give it a color. And that color could indicate which root it converges to. So functions such as this one that we started here, that is quadratic, will have two roots, typically two distinct roots. Functions that are of higher order will have multiple roots. For example, typically a function that is a polynomial of order n will have n distinct roots. And so you can give it a point indicating which root it converges to. And you can also say, you can also give it a shade. You can make it darker or lighter depending on how fast it approaches the root. That is, to achieve a given precision, you can make it darker if it takes longer, or lighter if it takes a shorter number of iterations. And so with that as a criterion, you can generate a very beautiful plot that will present many colors and with different shades. And what you will find, in fact, is a fractal. So the shape of this type of plot, where you give a color to each starting point depending to which root it converges, will give you the shape of a fractal. So I will leave that here. I encourage you to do that plot, to make that plot by yourself. Try to implement this algorithm. It's not very hard given all the formulas I've given you. You should also check the formulas, of course, for yourself, so that you can make sure I didn't make any mistakes, and see what you get for the plot. I hope you enjoyed this video. If you did, please consider liking and subscribing to the channel. And as always, if you're looking for a tutor in physics or math in English or in Spanish, you can contact me at shorttext331@gmail.com, or you can leave a comment in the comment section below, and I'll get back to you. And I'll see you next time.